Good morning and welcome back. Today we will continue our discussion about radiation due to localized radiation source, localized oscillating source. Last time we talked about electric dipole, and obviously today we will continue our discussion about magnetic dipole and electric quadrupole field. Okay, before we start, we will briefly review what we have learned so far. We learned that if we want to calculate magnetic field, all we need to do is vector potential A here. All we need to do is vector potential. Magnetic field B equals curl of A and H equals 1 over mu 0 curl of A. Okay? How about electric field? To calculate the electric field, we need the magnetic field as well as electric field. We need scalar potential and vector potential. We need two potential, not just one. However, in this section, it's an oscillating source. Scalar potential and vector potential are coupled together. That means we don't have to calculate scalar potential. All we need is a vector potential, A. And interestingly, electric field can be calculated from the knowledge of H field, and H field can be derived from A. So all we need is a vector potential. And we know this vector potential can be expressed as this form. Okay? That's equation 1. Mu 0 is a proportional constant, sum over L m. L runs from 0. M runs from minus L to plus L. This is a summation. 1 over 2L plus 1 spherical harmonic YLM theta phi exponential IKR over RL plus 1 times 1 plus A1 IKR A2 times IKR squared, and so on and on up to AL IKR to the L's order, and integrate the 3x prime, jx prime, r prime L, y L n complex conjugate. That's source coordinate. So it's prime coordinate. And r is always greater than r prime. Therefore, r is in the denominator and r prime is in the numerator. Last time we talked about L equals 0. Today we will talk about L equals 1. In this case, L equals 1. The coefficient A1 will be minus 1. So AX L equals 1 can be write into mu 0. L equals 1, so it's 3 here. It exponential IKR y squared. L equals 1 is still here. What else? 1 minus IKR, yes, here. Ym equals minus 1, 0, 1. L equals 1m. 1m. Okay? In this case, L equals 1. Okay? L equals 1. L equals 1. Okay. To be integrated. To be integrated. So summation, we can rewrite this part. We can rewrite this one because we will sum over L equals minus 1, 0, and 1. We will sum over these terms. We are going to use a property, summation property. We obtain this property in page 109 of Jackson. So let's expand YLM. L 0, L minus 1, 1 minus 1 is this one, 1, 0, Y 1, 0, 1, 0, this one. And last one, 1 minus 1, 1 minus 1 is this one. Quite similar except here. And this one plus this one, we got cosine phi minus phi prime. Cosine phi minus phi prime. Here we have sine theta prime. We can rewrite this one into this form. Just write it down. Interestingly, this one can be rewrite into cosine gamma. Gamma is the angle between source and observer. So gamma is the angle between source and observer. That's the angle. Here we have theta prime. And here, if this is the axis, we have theta here. Okay? And we have phi prime for this one. From the x-axis to here. And from the x-axis to here, observer, let's call phi, the angle phi. So we can rewrite this equation. We can move this summation to here. And then we can rewrite into 3 over 4 pi r prime n dot x prime. Okay? This is the angle. Angle is shown, n is shown here. X prime is shown here. Okay? So it becomes dimensionless. R prime over x prime. R prime is the amplitude of x prime. Okay? So this angle, inner product, this angle. So this one, x prime over r prime. Okay? So this equation can be rewrite into this form. This part, angular distribution can be write into this one. Then substitute this one into here. And we have r prime here. And we have r prime here. Cancel. We have a simple relations. In the integrand, we have these terms only. R prime is cancelled with r prime. And we have this one only. Let's compare once again. R 1 over r minus IKR. Okay, looks good. Looks good. And r prime cancel with r prime. Coefficient mu 0 over 3 exponential IKR over r squared. Here. Yes, the same. Okay? However, this one, we can rewrite this equation into this form. If we have triple product A cross B cross C, if you don't remember, we can use these properties again. Where is the notation? Oh, sorry, here. A cross B cross C. A dot C times B minus A dot B times C. And this time, A and we exchange this one. B cross C cross A. So we have a minus sign here. Okay? So we have a minus sign here. Okay? A times B. Okay? A times B. But there is a minus sign. So we have a minus sign here. Okay? So it becomes this one. Remember, J is function of x prime, source coordinate, and divided by 1 over 2, 1 over 2. And 1 over 2 we can rewrite into this form, minus 1 over 2. So cancel with this one is 1 over 2, 1 over 2. Okay? We can rewrite this equation. This equation can be divided into two parts. That is, this one can be rewrite into this one here, plus this one, plus, yes, move to the left. So it's plus, not minus. Okay? What else? This one, we already know this one. We met this one before. That is magnetic dipole radiation. Magnetic dipole here. Okay? But how about this one? Actually, we never saw these terms before. So we have no idea what is this term mean. So right now we can still define it AQ, electric quadrupole radiation. However, this term is quadrupole terms. Normally, if we have dipole terms, then we don't have to worry too much about high order terms. If we have electric dipole, we have magnetic dipole. We don't have to worry about high order terms at all. Yeah, we can skip high order term. So right now we have magnetic dipole, we have electric dipole. In fact, we don't have to worry about electric quadrupole, but we still write it down. Okay? AM is IK mu 0 over 4 pi N cross M. Why? N can move to the outside, so it will generate another minus sign. And what else? What else? N cross M. N cross M give us a minus sign. But remember, here we can divide it by IK, minus IK. So it moves to here. Move to the front. Move to the front. Here it generates a minus sign. And here we exchange the order. So another minus sign. Everything is the same. And here we will rewrite into N cross M. Coefficient the same. Coefficient are the same. no change at all. Okay, this one become n cross m. That's valid for kd. D is the source term, the dimension of the localized source, smaller than 1, and x is outside the source. So magnetic dipole is right here. That's magnetic dipole moment. We learned this one before. So AM gives the magnetic dipole contribution through equation 9.4 and 9.5. 9.4 and 9.5 tell us if we have AM, we can calculate H field directly. Curl of AM, we got everything. Okay? And then we can calculate electric field from the knowledge of H field. Let's go back to page 15 to 15. Oh, here, page 15 tells us that H field equals 1 over mu 0 curl of A everywhere, and E field equals IZ0 over K curl of H outside the source. So we have A now. We can calculate everything. We can calculate everything. Okay? You don't have to worry about this one. Just keep this in mind. We are going to use this one. As an user, we will use these properties. Okay? Use these properties. Okay, so in the far wrong means observer is very far away. It's much greater than the wavelength. So high order term 1 over r squared, 1 over r cubed can be cancelled. Not important at all. 1 over r is far more important. So we still have one term survive. No others. We still have this term survive. Okay? And high order term, obviously this one will be cancelled. Okay? So once again, we got this one and we got this one. We use these ones a lot. And by substituting here, we got pointing vector. And pointing vector per solid angle time average equals z0 over 32 pi squared k to the fourth absolute value m cross n. Okay, let's give the direction of E field, direction of EM. Okay, so P power, total power, is the integration of everything. Interestingly, P is proportional to k to the fourth. That means if the wavelength is large, then total average power is low. Its wavelength is small, frequency is high, then the radiation will be very large. K to the fourth is proportional to the wavelength, or inverse proportional to the wavelength to the fourth, or frequency proportional to frequency to the fourth. In the near wrong is still outside the source, but wavelength is greater than the observer. In this case, this one will dominate. Go back to the previous page. This one dominate. and this term dominant. So we can rewrite into this form. And interestingly, look at here, it's real, but we have an image. We have a I here. That means this is imaginary part, real part, imaginary part. E, M, and HM are 90 degrees out of phase. Average power will be 0, differed by I. HM has the same spatial patterns as that of static magnetic dipole in equation 5.56, but with exponential minus I omega t dependence. And B field energy much greater than E field. So unlike electric dipole, in the near field, electric field energy is greater than B field energy. However, in this case, magnetic dipole, B field energy is much greater than electric field energy. The electric quadrupole radiation discussed in 9.37 to 9.52 is more complicated. Here we will only illustrate its radiation pattern by the figure to the right. Quadrupole radiation pattern. It's not very powerful, not very useful for the electric quadrupoles. So don't worry too much. Electric dipole and magnetic dipole are far more important, and they have something, symmetry. And in chapter 10, we will talk about radiation due to M and radiation due to P. That's scattering and diffraction. I will show you how to excite M and P in chapter 10. Okay? Once we have M and P, we can calculate radiation field. That's it. We will talk about chapter 10 in 1 week. Okay? Now let's comparison between static and time-dependent cases. Static here. In static, the relation between rho J, E, B. Rho, we have rho, we will calculate E field. That's static. And we have J, we will obtain B field. One and only one dependence. One and only one. And in that case, the simplest expansion is 1 over x minus s prime. We can expand in many coordinates using the Taylor series. And Q is the volume integration. P is x prime times the charge density. Perform the volume integration. Quadruple term is here. And M is shown here. Okay? The definition of this one and this one are exactly the same as here. But the physical meaning will be slightly different. R dependence of E and B. E and B will proportional to 1 over R L plus 2. For R equals D, all the multiple field can be significant. But for R much greater than the source dimension, multiple fields are dominated by the lowest order non-vanished terms. That is, if we have monopole, electric monopole, then it will be much more important than electric dipole. Okay? And of course, we have no magnetic monopole. Therefore, magnetic dipole will be the dominant term. Okay? The time-dependent case will be slightly different. We row X. We need to, from row S, we can calculate Jx. And from row S and Jx, we can calculate. From Jx, we can calculate H field. From H field, we can calculate E field. Okay? Or you can start from here to calculate E field. That's the same. And this time, the green function becomes exponential ik x minus x prime over x minus x prime. There is no time-dependent monopole for an isolated source. So, note this term, because the average will be 0. And P, Q, I, J, and M has the same expression as those of the static counterparts, but with the exponential minus I omega t time dependence. In time dependence case, electric monopoles can generate B fields, and magnetic monopole can generate E fields. And once again, near Rome, this case, okay, R lambda always greater than D. Always. In a near Rome, quite similar. However, at far Rome, R is much larger than lambda, as well as D. In a far Rome, it will look like this form: exponential IKR minus I omega t. That's IKR. R is the radius from the origin to the observer. So they have something symmetry. This is the spherical EM waves. All multiple fields is inversely proportional to R. Relative power labels unchanged with distance. Okay, so that tells us many useful information. Jackson's equation 9.8 has some typo. This part is correct, but this one is incorrect. We should use binomial Taylor expansion. Using a Taylor expansion, the result should be this form. Expand. Let's consider this one very small. Very small. Okay. Okay, so we should use this one. A small correction. You can study by yourself. And let me show you a very interesting effect. In chapter 8, we consider waveguide and we consider cavity. And we mentioned if we have a waveguide, and we have a small opening, then the waveguide, it plays a role. The opening will place a role like electric dipole or magnetic dipole. For example, distortion of the tangential magnetic field here. Initially, we have H0 here. So we have this hole. There was some leakage here. That's the distortion of the tangential magnetic field. And in this case, initially, electric field is perpendicular to the metal. But we have a small opening here. So electric field can touch the other side. So this case looks like an electric dipole here. And this case looks like a magnetic dipole here. This magnetic dipole is opposite, is inversely proportional to H0. And electric dipole is proportional to P. Okay? Hambeth published a paper titled Theory of Diffraction by Small Holes in the Physical Reviews in 1944 during World War II. At that time, he has the military service as a soldier. He studied the radar systems. He wanted to study how to control the radiation direction, radiation patterns. So he used some small hole and found that each hole just like a little radiation source. By control the source and the phase, we can control the direction of the beam. That is phase array radar. And then later on, he won the Nobel Prize in 1967. Okay? Related to a simple but useful, very, very useful. Okay. How to generate electric dipole and how to generate magnetic dipole. We will talk about scattering and diffraction, a small particle or a small hole. But now, let's talk about antenna. Antenna. First, let's consider the simplest antenna, center fade linear antenna. That means FED, center fade. That means feed at the center. We feed the current at the center. FEED. A quantitative look at the center fade linear antenna. We have a very simple antenna, symmetry. Okay? And we have a transformer, two coil, primary, secondary. Okay? We have capacitor, we have resistor. Okay? We have energy source. Energy source will excite the oscillation. That's LC oscillator. LC oscillator. So the current will be much larger here. We can convert the source energy to transformer transmission line to here, and then same signal to here. So obviously we will generate current here. So on the other hand, current will flow from here. Okay, current will flow to here, and the other half, upper half this direction, lower half this direction. So later on, after half cycle, upper half will this direction, lower half will this direction. Conservation of charge. And this is a knot because nowhere to go. Charge will terminate here. So current will be zero. Current will be zero. So look at these figures. We have current flow in this direction and these directions. So looks like we have current. It will generate, according to Ampere's law, we will generate magnetic field circling around this dipole. So, and current flow to this direction, we will generate charge here. Current will generate charge here and negative charge here. So electric field will be in this direction. Magnetic field in this direction, circling around. Electric field from, so E field and B field are perpendicular. That's near field. At far field, E field will be in the same direction as this one, and B field will be perpendicular to E field. And so E cross B will be E cross B. E cross B in this case. E cross B is of this direction. Okay, E cross B in this direction. So let's correct. In a near wrong, E and B are principally generated by rho and J. So J generate B field, rho generate E field, respectively. Largely static field patterns. In a far wrong, E and B are regenerated through partial B, partial T, and partial E, partial T. That's EM fields. That's Faraday's law and Ampere's law with Maxwell correction. Okay? So let's give you a detailed analysis. The standard fade linear antenna is a case of special interest. We like this case because it allows the solution of 9.3 in a closed form for any value of KD. That means this one will have a closed form for any value of KD. D is the dimension of the antenna. K is the wavelength. Okay, how to do that? We will assume KD is smaller than 1. We will assume this one. And then J will look like this form. That's a reasonable assumption, but not necessarily correct. Okay. Why I say this is a reasonable assumption? Because we consider it a thin antenna, and thin antenna can be considered delta X, delta Y, because it's ultra thin. But in the real case, nothing is ultra thin, right? So it's good for far field, good for ideal case. Another one is at this point, no current. It's an open end, and the current has no place to go, terminate here. So current at this point and this point minus d over 2 plus d over 2 will be 0. So we can assume it's a sinusoidal. So at here, current will be largest, right? Current will be largest at the center and will be 0 at the two ends, this end and this end. Okay? So it's a reasonable assumption. Not the only assumption, but it's a reasonable assumption. By doing so, we will have a closed form. A will be simple. Okay? That's why we like this form. Because A is simple. A is simple, we can calculate B field and H field and E field. So J is symmetric about Z equals 0. Jx equals J minus G. It's symmetric. And I is the peak current. I is the peak current only when KD greater than pi. If KD is less than pi, I times sine KD over 2 will be the maximum value of this one. Okay? The antenna appears to be an open circuit. Open circuit. It's not a closed circuit. It's not a closed because it's not a circuit at all. How can this be a current flowing on it? So current flows in this direction in this direction or this direction, this direction or this direction. Okay, that's an interesting problem. Think about it. Okay, next one. So we have 2x minus x prime. Let me show you. That's the first one. That's the second one. Second one. So how to deal with this one? We can write it down. Let's assume the source in the z direction. So the angle will be theta. Okay, the angle will be theta. We assume the source just align with the z-axis. Okay, that can simplify the calculation a lot. Okay, and r squared, we can write r, and then this part can be considered as a small term. Cosine theta is n dot x prime. X prime in the z direction, n is in this direction. So we need to divide it by r. Divided by r. Okay? Because we have to divide it by r. So this will be a small value. This one, very, very small. 1/2. So it's the square root of this one. Now, I will recall the Taylor expansion. Square root of 1 minus x can be written into 1 minus 1/2 x minus 1/8 x squared. Okay? So the first terms is the same. 1 is here. I hope you still remember Taylor expansion. Taylor expansion. Expand this one with respect to x equals 0, with the center x equals 0. Okay? So the first one, we got this one. The coefficient is 1/2, and this one here. Second, 1/8 minus, and these terms. Okay? So r minus n dot x. What happened here? Oh, n dot x here. N dot x. What else? Plus higher order term. Plus 1/r squared here. R prime squared. Minus this one. R squared. 1/r squared. Other are very high order term. We can omit this high order term here. Okay? So we just keep this term here, this term here, this one and this one can be rewrite into here. Okay? Maybe, okay. So r x minus x prime equals r minus x dot x prime if r is greater than r prime. Looks like we have 1/2 here. 1/2, but never mind, because this is very small. Very small. Hence, if r greater than d, we can rewrite this one into this form. Simple approximation. Okay, in that case, ax is approximately equals ez in the z direction. Remember, because vector potential is lies in the z direction. Mu 0 I exponential IKR, okay, sine KD over 2 minus KDZ prime, just write in the z directions only. And in the denominator, we have R minus Z prime cosine theta. In the numerator, we have the phase terms. In the denominator, we have these terms. But this terms is in the denominator. Compared with this one is much more important. So once again, we can here just write this one into R. We make a lot of assumption, simplification. Simplify this one. We just calculate this one. Actually, we don't have to worry too much about other terms. We just calculate this one. Okay? Z prime cosine theta. That's Z prime in these directions. Simplify. Okay? Simplify the calculation a lot. So vector potential EZ mu 0 I exponential IKR over 4 pi. 4 pi, but here we have this one. Okay, this calculations is not very straightforward because we have Z prime here. We have another Z prime here. You need to spend some time, but eventually we got these solutions. It's an extra bonus. You can derive this equation by yourself. It's an extra bonus, okay? Try to derive this equation by yourself. I think it's not very difficult. If we make this assumption, and we make this assumption again, simplify a lot. So Z prime cosine theta in here can be negative if R is much greater than D, but Z prime in the phase part makes an important contribution to the phase angle, even at R greater than D, much greater than D. Once again, note is quite important. This part is far more important than this one. This part is sinusoidal part, change a lot. And this part always small, contribute just a little. So don't worry too much here. Next page. Okay, so in a far run, once again, the time average, we use 1 over 2, take the real part. Remember to take the real part. R squared N dot E cross H star, complex conjugate. And E is here. It's here. So eventually, the absolute value 1 of G 0 over 2 R squared H squared. Because after the manipulation, H cross N cross H complex conjugate, only one term survives. That is H dot H complex conjugate. That is the absolute value of H. And how to calculate H? H equals 1 over mu 0, curl of A. And A equals IK. This one will give us one direction in the N direction. IK. Curl is gradient. Others are constant. Remember, only this one survives. And this one. Vector potentials. Okay. Others independent of R. That still depends on the angle theta. Okay. So eventually, this one H gives us K sine theta, absolute value of A over mu 0. Mu 0. Okay. So by substituting here, z0 over 2 mu 0 square h squared. So we have mu 0 squared, k squared, r squared, sine theta squared times a absolute value squared. So substitute everything into here. We got these relations. z0 I squared over a pi squared absolute value. That's for r much greater than d and any kd. Okay? z0 I squared over a pi. So if kd equals pi, okay, good. kd equals pi. We have a simple relation. Equals pi. kd equals pi. Here, if kd equals 2 pi, we have another simple solutions. That correspond to half-wave antenna. kd equals pi, which means lambda equals 2d. Lambda equals 2d. That looks like an fixed end. Actually, it's open end. And another case, kd equals 2 pi, lambda equals d. Okay? Another one, lambda equals d. It's a superposition of two half-wave antennas excited in phase. Looks like we have two antennas and placed side by side. So it's most coherent. Unlike this one, half-wave antenna, radiation is strong, but pattern is very broad. However, if we have two antenna, 1, 2, then in theta equals pi over 2, that will be very sharp, narrow beam width. So the question is, can we control the pattern here and phase and pattern of this array, this antenna? So we can control the direction of radiation. Yes, we can do that. We can control the direction of the beam by change the position and the phase of the array. Okay, that's phase array radar. Finally, we will talk about this one. Once again. We can show you a simplified case. D pi over d omega. Actually, I will give you a lot of chance to practice. We will talk about this part in homework in more detail. So you can practice. That's very important because center fed linear antenna is useful because they are simple, easy to understand, and has a closed form by making some assumption. Okay, so here, once again, we assume R much greater than D and any KD. In the limiting case, dipole approximation, lambda is greater than D. Then, lambda is greater than D. That one is small. It equals 1 minus s squared over 2. S is smaller than 1. So cosine kd times cosine theta equals 1 minus kd squared, d squared, over 8 cosine squared theta. Cosine kd over 2 here. That is 1 minus kd squared over 8. So we can rewrite this equation again. The coefficients do not change. The coefficient does not change, it's still the same. And here, sine theta, the same. Denominator the same, but here can be rewrite into this form. G0 I squared over 512 pi squared kd to the fourth sinusoidal square. We have 1 minus cosine squared theta. So it's sine squared theta. Cancel. So eventually we have sine squared theta. That's valid for kd smaller than 1. This has the same k and theta dependent as in 9.23 electric dipole, which was derived by assuming kd smaller than 1. Okay, so this part is the same k and theta dependence as in electric dipoles. Okay, so we obtain the idea of electric dipole once again. Okay, I will stop here. We make some assumption. Let's have a look at center fade linear antenna again. Antenna simple and 0 here, 0 here. So the first assumption is kd is smaller than 1. The wavelength is smaller than 1. Okay? And second assumption is the current looks like this one. That's a reasonable assumption. By doing so, this one R, that's R can move to here, and here can be rewrite. So this one equals G prime. This one equals minus IK, and exponential term move to the front. And this part is actually quite easy to calculate. So it's an extra bonus. Please derive this equation and send your calculation to me. It's extra bonus, 1 point, 1 point. That's very important. Okay, and here is the note. So vector potential can be write into this form. Okay, depends on R, depends on theta, independent of phi, because it's symmetry, it's mutual symmetry. So obviously this one will independent of phi. And then we can rewrite this equation again. And for R greater than D, and actually is K, KD is small. Because of this assumption, KD small. Okay. So we just consider two interesting cases. KD equals pi, we have half wave antenna because D equals to half wavelength. And another case, KD equals 2 pi, we have another one. Okay, that's full wave antenna. And then we can calculate everything. We just go back to the simplest case. That's KD is very small. KD very small, and then we can rewrite into this form. Okay. I will stop here. Thank you very much for your attention.